So, hello everyone. We'll continue with the topic of modeling of time-dependent problems, and today I will talk about the transient heat condition as another example of time-dependent problems. And to simplify the configurations of our problem, we'll consider that we have a rigid solid body. It means we will not consider the deformations, considering only the heat flow from certain point to another point. So let's have an example of this. Take, for instance, or assume that we have a heat source, which could be like a laser beam or electrode, which is applied to a solid surface. This technology can be used in welding, as for example. And if you are putting your hand not so far from the heat source, you will notice that if we continue applying the heat source, the temperature at your hand or at your fingertips will increase and will keep increasing. By the time, it means we have a time-dependent process. And this process can also be modeled using, for instance, the finite element methods. As you see in this example, this is from our simulations, where we had a heat source here, which is moving. And you see that a little bit distance from the heat source, we have also an increase of in the temperature. And this is changing by the time, and we would like to know how we describe this process. So in order to derive the partial differential equation or the balance equation of heat transient in rigid body, so rigid body means we have no deformations, we will start with the balance of internal energy. This can be given in this form. I introduced this in one of the first lectures. The balance of internal energy includes thermal contribution and includes mechanical contribution, and it is a rate equation. So it's telling us that the rate of internal energy, which is rho multiplied by epsilon dot, and epsilon would be then the internal energy. So the rate of this energy or the internal energy equals to sigma scalar epsilon dot, and this is the strain and not the internal energy. This term is the stress power, which is connected to the mechanical response, and then minus divergence of Q. Q is the heat flux, plus rho R, so rho is the density, and R is the external heat supply. So this is the balance of internal energy in general. Now, due to the assumption of rigid body, the displacement will be zero in this case, or also the time derivative of the displacement means the velocity would also be zero. And for this reason, the epsilon dot, so the rate of our strain, is also equal to zero. So this the stress power term will be neglected, and then we have this simplified energy equation. In this, it's one equation, it's a scalar valued. It has one primary unknown, which is the temperature field. It's a function of space and time. So at each point in our domain, and at each time we would have, or we might have, different temperature. And then we need to solve this equation for a specific problem. So depending on the material, we have to specify our constitutive models. Namely, we need to specify first the energy function, so the Helmholtz free energy function, which is a function of the temperature. You remember this is comparable with the free energy for the mechanical process, which was the psi equals to half multiplied by sigma multiplied by epsilon. Here we would need to specify another kind of energy function. And then we have the entropy field, which is the derivation of the energy with respect to the temperature, and we have here minus sign here. This is like analogous to the stress, which was obtained by applying the partial derivative of the energy with respect to the strain. Of course, there are not similar quantities, but I mean the same methodology. And then we have this heat flux Q. In general, it can be a function of the temperature as the gradient of the temperature. We have also simplified formulation, which is the Forier's law, which then give us the heat flux as a function of the gradient of the temperature. So let's talk a little bit about the Helmholtz free energy psi. It's related to the internal energy. So we have seen that in the internal balance equation or internal energy balance equation, we did not see psi. We saw only the internal energy epsilon. And these are connected to each other by what's called the Legendre transformation. It tells us that the free energy psi equals to the internal energy minus zeta multiplied by eta, which is a thermal contribution. Now, if we take the time derivative of this, then it would be psi dot equals to epsilon dot minus, then we have zeta dot eta minus eta zeta dot. We have seen the definition of the entropy. It was the d psi to d zeta, and then we have d zeta to dt would be then zeta dot. So we have on the left hand side minus eta zeta dot, and on the right hand side we have exactly the same term, so they cancel out. And then we end up with this relationship, which is the epsilon dot, so the rate of internal energy equals to the temperature multiplied by the rate of the entropy. So this is equation number 3. Now, if we consider a particular relationship for the free energy, so for a simple case, we could specify this as is given in this relationship. So the internal energy would be equal to C, which is a constant. It's a heat capacity. We consider this as a constant, multiplied by zeta minus zeta 0 minus zeta logarithm of zeta to zeta 0. So depending on the materials, let's say this can be applied, for instance, for some metal material. And zeta would be then the reference temperature. Now, based on this, we can compute the entropy as a minus multiplied by the partial derivative of the free energy with respect to the temperature, and based on the energy that we have already specified, then the entropy would be C multiplied by logarithm of zeta divided by zeta 0. If we take the time derivative, then we have d eta to d zeta multiplied by d zeta to dt. And this equals to C, which is the heat capacity, multiplied by 1 to zeta multiplied also by zeta dot. Of course, we had used this rule for the derivation of the logarithmic function. Now we can insert this in equation number 3 to see that the rate of the internal energy equals to the C, which is the capacity multiplied by the rate of the temperature. And this simplifies the treatment very much. Let's talk a little bit about the physical meaning of some of the term. First, the energy storage mechanism. So we deduce from equation number 4, which we have already derived here. So it's exactly rewritten here, that the rate of the internal energy change, which is d psi to dd, equals to c d zeta to dt. It means the variation of the internal energy with respect to the variation of the temperature is a constant. And this constant is our heat capacity. Now, if we assume that we have a solid material and we are increasing the temperature, so we increase the temperature of our solid material from temperature zeta 0 to zeta, and we would like to see how much energy we have stored in our system. In this case, we just take the integration from zeta 0 to zeta, d epsilon to d zeta multiplied by d zeta equals to, again, the integration of from zeta 0 to zeta. C is a constant multiplied by d zeta. So if we apply this integration, then we end up with this relationship. So we have epsilon equals to epsilon 0, which is the heat capacity, which is the internal energy at the reference temperature, plus C multiplied by zeta minus zeta 0. What does it mean here? It means the incremental of internal energy and the increment of the temperature. There is a linear relationship between these two increments, and this can be plotted here. It means that the heat capacity, which shows here graphically, the heat capacity describes the energy storage for increasing of the temperature. So we have this linear relationship. So this is the first mechanism, which is the energy storage. The second mechanism, which is the heat conductivity. So heat conduction mechanism. So the heat conduction is assumed to be governed by the Forier's law. The heat flux is proportional to the temperature gradient. So we name this sometimes delta zeta, or we write explicitly gradient of zeta. The Forier's law is also a linear relationship. So you see here delta zeta, and we see here Q, which is a heat flux vector. And then we have a line between them. So it's an illustration in one-dimensional space. So would be then Q equals to minus kappa multiplied by gradient of zeta. And kappa, which is a positive parameter, is a heat conductivity. And as the assumption that the heat flows from the hot to the cold material point, that's why we need a minus sign here. And this is also results from the evaluation of the entropy inequality. Now, if we have specified the heat flux, now we can, and also the relationship between the rate of the internal energy with the rate of the temperature. Therefore, we can insert equations number 4 and 5 into the original internal energy equation, or in the original energy balance equation, which give us now a simplified form for the energy equation for rigid body. So we have no contribution of the mechanical deformation. This is a first order ordinary differential equation. We see here we have zeta dot, and we have here zeta, and some other terms which might be also depending on the or changing by the time. But what's important is that it's a first order ordinary differential equation, and it has exactly the same form as we have seen in connection with viscoelasticity. It has the form y dot equals to fy t, a function of y and t, and simply y would be then, in this case, is the temperature field. If we have time-independent process, so this is what you would see, for instance, in the case of steady state heat conduction, then it will be then zeta equals to 0, and in this case we'll have something like this. In steady state, if you are applying the simulation of steady state, you put your boundary condition, and in one click you'll have like a temperature distribution. It's not a time-dependent computation. But in our case, we have a time-dependent process. And we would like to integrate this equation, which is a first order differential equation. We would like to integrate this numerically and in time. So we can use exactly the same methods that we have discussed in the previous lecture, which are the implicit and the explicit schemes, also the one-step and multi-step schemes. Let's consider first the forward or explicit Euler. So we have this form y dot equals to a function of y and t. By forward Euler or explicit Euler, then we have yn plus 1 minus yn divided by delta t equals to our function then will be evaluated at the previous time step. So we'd have yn and tn. Let's recall our balance equation. Then we have zeta dot equals to kappa divided by rho c, divergence gradient of zeta plus rho divided by c. Now for zeta dot, if we compare this by zeta dot, then we would have zeta n plus 1 minus zeta n divided by delta t. And all the terms on the right-hand side of our equation would be at the previous time step. So we would have then here zeta n, which is the most important. And then if we have an external source, which is a time-dependent, then we'd have also this source from the previous time step. So it would be Rn. Okay, so if we take the alternative scheme, which is the backward Euler or the implicit Euler, then we start from the same form of the ordinary differential equation. We apply implicit time integration scheme. The left-hand side would be exactly the same as before, so we would have like yn plus 1 minus yn divided by delta t. The right-hand side, or our function, is evaluated at the next time step, so we would have yn plus 1 and tn plus 1. Applying this methodology to our energy equation, it would be then zeta n plus 1 minus zeta n divided by delta t. So this is the first part. And the rest of the equation will be discretized at the next time step. It means that we have kappa divided by rho c equals to divergence gradient of zeta n plus 1 plus rho n plus 1 divided by c. As you see, it is a nonlinear equation because we have here zeta n plus 1 and we have on the right-hand side also zeta n plus 1. So we need to linearize this equation in order to get some kind of explicit relationship where we have on one side our unknown would be zeta n plus 1, and on the other side we have the known values which are coming from the previous time step. So this is what is connected with the computational constant in our case. Alternative to these two methods, we could also apply the Crank-Nicholson trapezoidal rule, which combines information from the previous time step and from the next time step. Exactly, it can be applied to first-order differential equation of this form by taking yn plus 1 minus yn divided by delta t, so exactly the same left-hand side term. And then the function will be at the previous time step and the next time step, which is multiplied by half, so the average. If we apply this idea exactly to our energy balance equation, the left-hand side, then zeta n plus 1 minus zeta n divided by delta t equals to half, then the evaluation of our function at the next time step plus and the evaluation at the previous time step. So we'd have here zeta n plus 1, and here we have zeta n, Rn plus 1, and Rn. This is how we apply this Crank-Nicholson or the trapezoidal rule. If we want to apply this backward differentiation formula of second order, which is as I said in the Flex PDE, then it will be for the left-hand side. Then there is some change because this is multi-step method, so we need information from two previous time steps. Then it's formulated as follows. So we have 3 multiplied by zeta n plus 1 minus 4 zeta n plus zeta n minus 1 divided by 2 delta t. So this is the left-hand side, and the right-hand side would be then at the next time step. So then we have here zeta n plus 1 plus Rn plus 1. As you see, this is the zeta n, so previous time step, zeta n minus 1, it's 2 previous time steps. And this is an implicit formulation because we have zeta n plus 1 on the left-hand side, and then we have zeta n plus 1 on the right-hand side. So we need to linearize this, but in Flex PDE this is carried out automatically, but it's important to know what's going on in the background. Okay, good. So with this, I'm at the end of this video. Thank you so much for the attention, and then we'll meet on Monday in the lecture. Thank you so much.